Welcome to some electricity. We're gonna look through a simple circuit, okay? Now, I know we've done them before last year. I'm just going to recap over that and do some examples before we get to the internal resistance, which is the next one. So let's just look. What is the objective of all of this that we're doing? We're looking to be able to solve a circuit. They're going to ask us questions. What are the readings on ammeters, voltmeters? How much is this resistor, etc., etc., etc. Now, there's a few things that we've got to do. The first thing that we've got to conceptualize is that we need to break our circuit down into a simple circuit. So what do I mean by a simple circuit? I mean, in essence, this. One source of voltage, okay, one resistor, and that, okay? And I'm going to put a voltmeter over here, and I'm going to put a voltmeter over there, like that. Now, just before we carry on, voltmeters and ammeters, remember, are in line. Ammeters have very, very low resistance. Why? Because you want all the current to go through it. You don't want it to in any way impede the flow of electrons. Voltmeters, on the other hand, you don't want any current going up there at all. So voltmeters have a very high resistance so that we don't get any current flowing through them. Okay, that's essentially the difference between the two. Probably a question that's going to come up. Just remember it, but it's actually logical common sense, isn't it? Right, so what do we do here? We say we need to break our circuit down into a simple circuit that looks like this, right? Now, what are we going to get? We're going to get a whole bunch of things, all right? And so what do we say? Let's say, for example, they say to us, this R is equal to 15 ohms, and the voltage on the battery is equal to, let's say this is 3 amps over here. All right, for those of you who did it before, we always put in the current I, correct? And they've given us I equals 3. So what do? I go back to the only formula that you have to use in these. They're all given to you anyway, but the only one, you say V is equal to I, which is 3 times 15, which is going to be, I think, 45 volts. So this is going to read 45 volts, which means that there must also be 45 volts. Why, you ask? Why must the volt? Well, it's quite straightforward. We've got one source of voltage in our circuit. We've only got one battery. So all the voltages in the circuit themselves must add up to the voltage of the battery. There's only the one. We don't do multiple power sources into circuits, okay? That we're going to do, we're going to cover that in A levels when we talk about Kirchhoff's laws. But we're not going to do it here. So all we got to remember in our minds is, hang on guys, we've only got one source of voltage, aka EMF, but we'll get to that in a bit. So if I say that the voltages across the circuit, throughout the circuit, must equal the voltage of the battery, the V source as well. That we could also call V source, spell it correctly. Okay, now, why? Well, we say, okay, in any circuit, what can we have? We can have resistors that are like this, can't we? All right? We can have resistors like that. All right? Those are in series, aren't they? They are in series. We're just recapping and going through this quite fast. In series over there, if I say to you, this is 2 ohm resistor, this is a 4 ohm resistor, and R3 is equal to X, okay? And I tell you that we've got a 12 volt battery, like so. All right, I haven't put switches or things in. So we've got that, all right? Now, what do I do first? Step 1, we always put in the current from positive to negative, and we label it. I goes through there, I goes through there, I goes through there. So in other words, the current is going through each one. Think about it like water. It's got nowhere else to go. So it must flow through each resistor one after the other. All right? When we get splits, we'll get to that one. All right? So now, let's have a look here. All right? Let's put V, a voltmeter, over there. Let me put a voltmeter over here. All right, and let's put another voltmeter over there. All we're doing is we're reading the voltage across each resistor, okay? Now, the last thing is I say, this is a 12-volt source, okay? 12-volt battery, whatever we want to call it. What are we going to do? Well, first thing we say is these voltmeters here are going to read. Oh, hang on, I don't have the total resistance. What do I know? Well, now we start the process of solving a circuit. What do we do when we're solving a circuit? Go to where you've got the most information. There's only three things you need. Okay. Firstly, look if you're given. So step one, look to see if we have all resistance in circuit. If we have all the resistance in the circuit, calculate R total. Okay. If they're in series, remember we add them. If they're in parallel, we go 1 over is 1 over equals 1 over plus 1 over, correct? We're going to do one now, so don't stress about it. But that's the first step. Here, no, we are not given the total resistance. So we can't go and calculate it anyway. So what do we do next? We say, okay, step 2, look for, shall I write it down over here? Oh, come on. You're supposed to go up. Step 2, okay. Look for 2 out of 3. What 3? V, I, R. Okay, that's it. So now let's go back to our circuit up here, and let's see. Well, what do we know? Do we know V? V1, V2, V3, V equals IR. Okay, let's say they tell us that I is equal to 1 amp. Okay, so now we know that. So in each case, we can go, hold on, can I work out V here? Yes, V equals IR is equal to 2 times 1, which is equal to 2 volts. Over here, V is equal to I, which is 1 times 4, which is 4 volts. V, crash and burn, right? What do I do here? I can't work it out. All I can say is it's equal to 1 times R3. You say, okay, now can I calculate V? Aha. What did we say? We said the voltage, the total voltage, V source, or V input, or whatever you want to call it, your battery voltage at this stage, until we do internal resistance, is equal to V1 plus V2 plus V3. 1, 2, and 3. The battery charge must be equal to the voltages across all the others, right? So we say the V source, 12, must be equal to 2 plus 4 plus V3, and you can now go and work out V3 as being, V3 comes out as being 6 volts, I think. 6 volts, I think I'm right, okay? Just see, done the thing, yep, 6 volts. Therefore, R3, so now I can go and say you are 6 volts. And remember, as you solve the problems, the I, the voltages, the values of R, put them onto your circuit diagram. Don't leave them in the text, because you will forget that you've solved it. It's human nature. You move on. So put them on your diagram. The same goes for all of our physics problems, okay? When you've solved for something, put it back onto the diagram, okay? Critical, because then you don't have to worry. It's right there waiting for you to use it. Because guess what? When you've solved for that, the chances are you're going to use that to get to the next answer that they're going to ask you. It's a process of working through. The other thing is they ask it in a certain way. I am not doing that here. I'm just going to say solve the circuit, and we just find our own way through it. But generally speaking, they tend to lead you on a process to say, find this, then find that. Usually one uses the previous to get to the next. Very similar to geometry. Once you've solved this, you then use that to move on to the next. Right. So V3 is that. Therefore, you go to V equals IR for this component, for R3, which is a component, and we say that 6 is equal to 1 times R. Therefore, R is equal to 6 ohms. And I go back and I put 6 ohms up there. Very straightforward and no hassles with that. The last thing we need to talk about this circuit over here is let me just do it in red. If you've got resistors in series, a series is called a voltage splitter. Right? We've been through these before, but it's a voltage splitter. Okay? It's going to split our voltage up. The next that we get is we get resistors in parallel, correct? Now, what I often do here is I generally use a ghost resistor. I call it with my students a ghost resistor. So let's put in a current first. Well, the current's coming along here. What's it going to do? It's going to split I1, I2, I3. Now, it splits in what ratio? What is a resistor? A resistor is resistance to flow. Think of it as a hose pipe, right? Is the water going to flow through freely if you squish it? No, it's not. Therefore, the bigger the resistance, the less the current, right? In other words, the greater R, the less the current, because you're stopping it. That's all it is. You are stopping it physically. You're squishing the hose pipe, it can't flow. And what is current? It's a flow of electrons through the circuit. That's all this is about. So we say, okay, obviously now we have to label these, so let's just label them over here as R1, R2, and R3. Okay, so yes, there is, and for those of you who want to, you can go and work it out on a ratio basis. What do? I have to find the equivalent resistor. I call it with my students, I call it the ghost resistor, the effective resistor of those in parallel. And what is the formula? 1 over R parallel is 1 over R1 plus 1 over R2 plus 1 over R3. Okay, there you're given that formula again. But that's what it is. Okay, so what does it mean? It means I can calculate R effective if I know R1, R2, and R3, don't I? Okay, let's just look at this and say, okay, fine. This then is going to do what? Well, this over here is resistors in parallel, correct? Okay. Oh, come on. Okay, make page 2 and put this in. This is, just see if I can slide. Well, not really. But I think if I just take it down a little bit like that, we can talk about it. I'll put it into red. Shall I put it in blue perhaps? In parallel. Okay, resistors in parallel is a current splitter. Therefore, voltage is constant. I'm going to explain what I mean now. What it means is if I go and I put a voltmeter here, if I put a voltmeter there, or if I put a voltmeter there, or if I put a voltmeter when I've worked across there, they are equal to each other. Their voltage across is the same because you've split the current. What does that have as its implication for series? It splits the voltage, therefore the current is constant. Now that's not too much to remember, is it? I'm sure it's not, no. So therefore we've got that situation now, and we can work it out depending upon what we're given. We're going to pile into an example now. Now up here I said, right, now the ammeter and the voltmeter, I've spoken about it before. Ammeter is in line, okay? You put it in line. Why? Because you are measuring, think about it, what you're looking at is how many electrons are flowing past. Why? Because what is current? I is equal to Q over T. And what is Q? Q is coulombs, which is charge over time. And charge is number of electrons over time, isn't it? And each electron is going to be n times 1.6 times 10 to the minus 19 coulombs. So it's measuring how many electrons. It's counting them as they go past, isn't it? That's what the ammeter is doing. The voltmeter is measuring the potential difference across each side. Okay? The voltage drop, if you like. But let's just keep it as just the voltage across that. Okay? So that's the terminology that we're going to use. Now, and obviously a voltmeter has very high resistance, as I've said before. Why? Because you don't want any current going through the voltmeter. All right. Let us now have a look over here. We've spoken through that. And let's look at an example, shall we? I think that's probably the best way to do it. And then we'll go through the recipe piecemeal with it. Let's take an example here. And now a battery could be shown as individual cells. I'm not going to go through all of that again and again. There's an ammeter given over there. And let's put in a resistor here. And let's say, for example, we go up to another resistor over here and down to a resistor down here. And we're going to have ammeters and voltmeters and stuff. And we say this is 3 ohms. This is 10 ohms. This one is 6 ohms. And we're now going to go through and solve the circuit. All right, like so. I haven't put in switches. And I say V equals 24 volts. They could have said to you there's a voltmeter V1 over here which reads 24 volts. Okay? That's the same thing as saying V of 24 volts at this stage. Okay? When we get into the next bit, there's a little bit on internal resistance, which is not really too difficult to gather. So what do? All right. Step 1, am I given the total circuit? Am I given all the resistors? Yes. Therefore, work out total resistance. Okay. How do I start? Well, we start with the parallel pair, and here's what I call with my students a ghost resistor. What do? I work out the value of that. So I say, what do? I say the parallel pair, okay, or like that. I say 1 over R is going to be 1 over 3 plus 1 over 6, which is equal to 3 over 6. Therefore, R effective is going to be 6 over 3, which is equal to 2 ohms. And I go and I put that in as a 2 ohm. Right? Please don't forget, I know I said it in the last sequence as well, don't forget that inversion. Okay? That's where the mistake occurs. Students forget to flip it over. Okay? So I go and I put it in. Okie dokie. Next, I can say, right, I've got that. Therefore, okay, now I carry on and I say, cool, I know that. Therefore, circuit resistance or total resistance. Total resistance is R. I've now got a 10 and a 2 in, one behind the other, haven't we? What did I do here essentially? I took the 3 and the 6 away and replaced them with a 2. That's what we did, isn't it? That's this process. We're taking all of those away and replacing it with 1. Now I've got a 10 and we've got a 2 in series. We add them and we can cut them out and replace them with a 12. 10 plus 2, which is equal to 12 ohm. So this is going to be equal to V total or V circuit. Now, we've got a simple circuit, haven't we? Yes, we've got a battery, 1 V source, and 1 resistor. Therefore, I can say V equals IR. V, do I know? It's 24 volts, is equal to I times R is 12. Therefore, I is going to be equal to 2 amps. What do we do with that? Okay, what did I not do first off? I broke my own rule, right? I did not put in I. Okay, I1, I2. You put it in by every component, including the meters, the ammeters, right? There it is. So I now know what I is, and I've said that I is equal to 2 amps. Am I right? Okay, let's just check it. I said I was equal to 2 amps. So we now go and we put it in as 2 amps. Okay, what happens over there now? Now we've got to go and split that guy up, haven't we? All right. So I say it's 2 amps. Now what do? You go back to each component. All right, black. Now go to each component in turn. Okay, and work out what's remaining. Let's see if we can do that. Okay. I'm sure we can. Well, what do we do first? We first of all go to the 3 ohm resistor. Okay, we go to the 3 ohm and we say V equals IR for that one. V do we know? Oh, hang on. V is I times R. But what is the voltage over there? Do we know what it is? Well, here, do I know what the voltage is there? Yes. I first got to go to this guy, haven't I? And I've got to say, hang on, the voltage over here is going to be equal to I times R. So V over here is going to be 2 times 10 is 20 volts. Then I can go and say, what is my voltage here? My voltage is 2. Remember, 2 amps are going to flow through that because this is my effective. It's the ghost resistor. So therefore, it's 4 volts. So I can go and say 4 volts and V is equal to 4 over there equals 4 volts. Okay. The other way was to say, hang on, 20 volts, so the total across the parallel must be 4. In the circuits, there's very often different ways of doing it. You can see it. I could have said using the ghost resistor, which is very often a very useful and a quicker tool, especially if you've got multiple resistors there, I guess. So what do? I say, hang on, 20 plus the total voltage across these two, and it's the same because it's a current splitter. Therefore, I have got my answer as 4 volts. Now I can go to each resistor in turn, and I can say, yes, I know. V over here, 4 is equal to I, and that is going to be I1 in this case, I think, times R, which is 3. Therefore, it's going to be 4 over 3 amps. Right, let me just get another page. And the next one, the 6 ohm component, you say 4 is equal to I times 6. Okay, therefore I is going to be equal to 4 over 6, which is 2/3 of an amp. Therefore I total, remember your current must add up again, is going to be equal to 6 over 3, which is equal to 2 amps. So it is correct. Next, I'm going to tackle a problem which is the quintessential light bulb problem. You are asked a circuit like this. Okay, this is where they talk about power. Okay. Consider the following. It's an example. Okay, and it is the light bulb. Oops. The light bulb problem. All right. What do I mean? Well, we get circuit 1. Circuit 1 looks like this. Just basically a battery like that, just to push some charge around. And we're going to have a light bulb there, a light bulb there, a light bulb there. And they're going to ask us various questions about this circuit. Okay. And we're going to do that. Step 1, let us put in our current. I flows there, I1, I2, and I3. Now they say, the question is how brightly do they glow given that each of those bulbs is the same. Generally speaking, when you've got a circuit, most bulbs are the same. Right? Think of a whole tree decoration. The bulbs are generally all the same kind of bulbs. You don't often put in different ones, well, because they're voltage rated, aren't they? Okay, when you buy a bulb, it's for a 240 volt or a 12 volt or whatever voltage it is. And they give you a power rating very often. Now, please remember brightness is equal to power, which is equal to V times I squared R, or V squared over R. You are given these as well. Okay. Now, we've put in the current, okay? Now, let's just go through the logic with me here, okay? The current is coming along, and it's going to split into 3. What ratio does it split into? Remember, we said the resistance of the bulbs, they're identical bulbs, which means the resistance is the same. This is R, R, and R. So you say let resistance of each bulb be equal to R ohms. Right? So the current is going to split equally. I1 equals I2 equals I3 equals main I divided by 3, is it not? Okay? You should be able to see that. Quite straightforward. All right? Now, so we've split it up, and they are the same because the resistance is the same. And remember, it's going to flow according to the resistance. If there's no resistance, the current's going to go that way, like water does. All right? Now, remember, power is equal to I squared R. Okay? Now, in this case, the power, let's say power in bulb 1 is equal to I1 squared times R1, is it not? But that is the same as I over 3 squared times R1. And R1 is the same as R2, as R3. And the I going through is the same in each case. Therefore, the power in bulb 1 is equal to the power in bulb 2 is equal to the power in bulb 3. So they all glow equally brightly, don't they? Let us work out the total resistance, shall we? All right? Just another way of doing it. Let us say the total resistance. So let me just go down a bit or up a bit, whichever way. You've obviously got the sketch in front of you. I'm sorry it's disappearing off screen. I can't hold it on screen and do the work. But you should have it on screen or on a piece of paper there, drawn. What do? I say, okie dokes. Now, yes, I said, okay, I've got the 3 resistors. Okay, so 1 over R effective is 1 over R1 plus 1 over R2 plus 1 over R3. But they are all the same resistors, aren't they? They are all so many ohms, which is R, which is going to be 1 plus 1 plus 1 is 3 over R. Okay? Therefore, okay, the voltage in the battery is equal to IR for the circuit. Therefore, I for the circuit is going to be V over R, which is V over 3 over R, which is equal to invert and whatchamacallit, and I'm sorry, 1 over R is that. Let me just finish this off here. Okay, you can see, just change that. That's R over 3. Because R effective here is R over 3. So I've got that over R over 3, which is equal to 3V over R. Is it not? So the current coming along here, let's just go back. The current coming along here, I'm going to put it in red. The current at that point, I, is equal to 3V over R. Okay. If you get confused by me not using digits, call each resistor 2 ohms and call the battery 12 volts. Assign it a number and work it through like that, and you'll see what I'm talking about. In fact, that's a good way right at the end. I'm going to put in some hypothetical numbers anyway. But just call each resistor 2. Don't use 1. Right? Call them 2. And then when we do the other circuit, call them 2 again and keep your battery as 12. Why am I doing? Because those are simple numbers to divide. All right? So I is equal to that. So I1, I2, I3, it's going to split into 3. Therefore, I can say, just let me get back to black. Therefore, I can say that I1 1 is going to be 1/3 times 3V over R, which is going to be equal to V over R. All right? And in each case, I2 is the same and I3 are the same. Therefore, the power in each bulb is going to be equal to I squared R. Let me just complete it. Can you see I'm doing it both ways here, right? Is equal to I squared R. I, going through each one, is equal to V over R all squared times R, which is equal to V squared over R squared multiplied by R, which is equal to V squared over R. Okay? And it's the same in each case. Okay. That's just proving it for one way. Now they say to you, so in other words, each one glows equally brightly. Okay, if they are in parallel. We've proved it. Please go through this. It is going to be a question without a doubt. Usually it'll be either this way or it'll be the one where they split the other way. The next section of this is to say, right, what happens next? The next set is what happens if lamp number 2 blows? Let's go and pop lamp number 2, shall we? Okay. I said lamp number 2 is here, and blue, I was going to highlight that as lamp 2. That's going to be lamp 1, lamp 2, lamp 3. Okay. Now that one blows. What happens now? Well, you just go back to your circuit, or please bear in mind, it doesn't necessarily pop. Maybe there's a switch. So what they could also say is that you open the switch just before lamp 2. What happens? If the switch is open or the lamp blows, you've got no current flow. So what does our circuit become now? Our circuit has become this, right? Has it not? Our circuit has become that. Lamp there, and this one has gone. Well, let's have a look. What stays constant? V. It's the same battery, right? So V is constant. R stays the same like that. Let's now go back to basics and put in our current. I1. Now we've only got I2, haven't we? Let's now work with the circuit. I'm just going to do it next door. So let's have a look. Can we do a ghost resistor here? Okay, can we put it in? Yes, we can. What is it going to be? 1 over R parallel is 1 over R plus 1 over R, which is equal to R is the LCD, 2 over that. So R parallel is going to be R over 2. Therefore, V equals IR for the circuit, because this now is R over 2. Okay? What is V for this? Well, V is constant. It didn't change. Same battery. Okay, you'd call that your 12 volts if you assigned a number. Okay, this is really a good one to go through. So let's have a look here. We say, okay, V is the same. So what's my new current? Is going to be V over R, which is V over R over 2, which is going to be 2V over R, correct? Therefore, it splits evenly again. So what is my current? My current is equal to I1 is a half times 2V over R, which is V over R. And over here, it's also equal to V over R. You can see where this is going, I'm sure. So what has happened? What has happened is this. Is once again, the power is equal to I squared R. What is I? I is V over R squared times R, which is V squared over R squared times R, which is V squared over R. And guess what we've got here? We've got the same as before. It's the same as before. So if they are in parallel and one blows, or you switch it out or switch it off, what happens? The current adjusts. Because the resistance has changed, the current changes, and it adjusts to keep the brightness the same. All right. I've come to the end of the time. In the next session the next one. I'm going to continue with this problem, and I'm going to do another problem as well. So it might be a bit shorter, but we'll go through finishing this problem where I'm going to do different circuits, right? I'm going to do series ones and then a combined one, just to show what happens. So please, when we look at the next one, just keep this problem and let's move on to the next one. I apologize for splitting them. I don't normally do that, but in this situation, I'm afraid time has become our enemy. Cheers, thanks for watching, and let's go on to the next one, and let's do it concurrently from here to the next one, so that you've got one set that works through this type of problem. Cheers, see you in the next one. Bye.